We will not be testing you on percent yield or percent purity. Nope. Because I can't teach it today. I want tomorrow to be a little bit of review, and then Monday is your test. Hello.
Yeah, I wanted to talk to you about the test if you don't have time.
Okay, we can do it later, but I've got to teach the class right now. Okay? Yeah. Yeah. Okay. All right. So obviously we have done 7.1a, 7.1b, c, and d. We have not done particle stoichiometry, gas stoichiometry, mixed stoichiometry. Like, I feel like you could do it, but I'm not going to worry about it. Okay? So I'm just going to leave that, but you should be doing the titration review. Okay? You should be doing the titration review. What on earth is happening in that hallway? My God. Okay. Yeah, actually, Zenny, thank you so much. So that's our basic stoichiometry. Limiting reactant, all of it. One of the things that you haven't done yet is the one that has simple stoichiometry and limiting reactant problems. After we've learned our little lesson today, that might be a good thing to work on, okay? Because you don't want to be trying to do limiting reactants when it's just regular. And you don't want to be doing, simple stoichiometry when it is a limiting reactant. So part of it is recognizing, did I give you one reactant quantity or did I give you two reactant quantities? Okay? So we're skipping percent yield and percent purity. I will, if we have time, like maybe next week, Thursday, Friday, whatever, I'll teach you that. But you will survive Chemistry 12 without it. Enthalpy and stoichiometry, if you want to, you can do this as an enriched kind of thing. Okay, enthalpy and stoichiometry. In fact, if you wanted to do percent yield as an enriched thing, you could. I'll have like an enthalpy thing and a percent yield thing. They're just optional though. Electrolytes and non-electrolytes. So we are doing that today. We're not going to do ion concentration. Okay. We have done ionic reactions double replacement. We will not be doing single replacement. I would say with these dilutions, we're not going to do them before your test. However, diluting is a skill that most people are kind of like, the first time, right? It's never something people are the most happy with. And this actually gives a couple different techniques. So I might hit on that again next week if we have some time. I would like to hit on those. So basically what we're looking at is we are looking at most of 7.1, all of 7.2, most of 7.5, and just the first of 7.6. Okay, I will also put those up on Teams. Okay, but that's where we're at for Monday's test. All right. So today we are going to go to page 92, 7.5c. This is dissociation and versus dispersion. Okay. Page, let's see, is it 92? No, it's page 90. Page 90. The table of contents is messed up for the last sections. Okay, it's like 2 pages higher than it should be for the last couple sections. Anywho, page 90. You need to be able to recognize ionic and molecular compounds, which hopefully is not too hard. Ionic compounds begin with a metal or NH4. So what you're going to be doing for this first little bit is you're going to decide whether it is ionic or molecular. You're going to write an I and an M. Step 2, you are going to recognize acids. Okay, so you're going to go back to question number 1, essentially, and you're going to pick all the molecular compounds that begin with an H or end in COOH, and you're going to circle those compounds in question 1, which are acids. Okay? After that, you are going to write the dissociation equations. You are responsible for writing dissociation equations on the test. So, basically, everybody comes apart. If you have 2 ions, you need a coefficient of 2. All right, this is on page 90. Still on page 90. Is it not on page 90? Okay, good. Phew. Okay. Acids dissociate, ionic compounds dissociate. So what that's going to look like is on our next page, page 91. If we take NaCl, it's going to split apart into Na and Cl. This is very much like what we were doing with your ionic reactions yesterday. You separate it into Na. You need to have the charge. And you need to have aqueous. Cl, you need to have the charge and you need to have aqueous. If we have Fe2SO4 3, you need to say that there are 2 Fe's by putting a coefficient of 2 in front of the Fe. Like I said, it's very similar to what you were doing in the ionic reactions yesterday. But these are the dissociation equations. Basically, you have to have the dissociation equation happen before you can have an ionic reaction happen. Dissociation has to happen first, and then the ionic reactions can happen second. But with less steps. It would have made more sense to do this first and then the ionic reactions, but today is such a short day. I'm like, this is a short topic. We're going to do this one today. Yeah? Acids. You need to take apart the H from the rest of the compound. And don't forget, you need to have the charge and the aqueous. And if you have an acid that is the COOH type, remember it is that last hydrogen that is the one that comes off. And then people always want to know, well, what the heck is the charge? I mean, if it's acetate, that's great. I know that the charge of acetate is -1, but what if I had C4H9COOH? What if I had that? They're always going to be -1 because they're always with a +1. Okay, so don't get confused by that. Whatever it is, C4H9COO minus, that's going to be a -1 because the H is a +1. Okay? So you're going to write the dissociation equations for these ionic compounds and acids. And then finally, what you're going to be doing is you're going to be writing the dispersion equations. Tell your partner what we mean by dispersion. I got really graphic with my other block. I think it was block 8. I was like, if you dissociate, it would be like if you had a bunch of people and they like cut themselves in half and one half went this way and one half went that way. And then every half, little half people wandered around. If you disperse, everybody's in a crowd and then just everybody walks off. There's no splitting in half. Okay? Which is not a lovely picture, but it sticks, right? So in dissociation, you might have 2 arms come off and then you've got a body, right? Or, whatever. In here, the entire person stays intact. Okay, so in dispersion, you start with some CH3F, which would look like this. CH3F, and it might be next door to another FCH3, and then they would just separate from one another. CH3F, CH3F, separate.
So like with sugar, for example.
Yeah.
They're
Yeah.
not actually like
There's no dissociation. When you have sugar in water, sugar is C12H22O11, and it is a solid. And when you put it into water, it is still C12H22O11, just now it is aqueous because every molecule is separate from every other molecule. Yeah? So when you write the dissociation equation, the only thing that's the same as the dispersion equation is that you have an aqueous product. The product is always aqueous, and that's it. And other than that, the formula stays the same because it's not splitting apart. Like the actual compound itself is not breaking apart. All right. And I think that's it. Recognizing electrolytes and non-electrolytes. Basically, if it is ionic or if it is an acid, it is an electrolyte. If it is molecular, but it's not an acid, that is a non-electrolyte. How do you know if it's ionic or an acid? That's going to start with H+, NH4+, or a metal. Or it's going to end in COOH. So those are all your electrolytes. We've gone through this before, but it bears repeating, okay? So I think with that, you would be able to recognize your electrolytes, your non-electrolytes. You'll be able to write dissociation and dispersion equations. So you guys are going to be working on pages 90 to 93. And if you finish that today, then I would say probably your next best thing to do is go do the titration review, which is on pages, where's our titration review? Page 42 to 48. Yes.
So acids are molecular compounds.
Yes.
But then
They dissociate into ions. Isn't that irritating? Yes.
But why?
But why? Because hydrogen is funny. Yes. Because it's a non-metal, right? But it is super small.
Oh.
Okay, so its smallness makes it behave strangely. Yeah? Because what's going to happen is when it forms a bond, like if you have, I don't know, did we talk about electronegativity at all? Not very much. Okay. Some atoms have a strong pull on electrons than others.
Right.
Okay. So if you attach hydrogen to say oxygen, the electrons in between them are going to spend more time closer to the oxygen.
Right.
So there's going to be a greater electron density of the oxygen, which means that if you put the hydrogen into water, you've got this little proton with no valence electrons. So it's a little tiny positive charge. In fact, it's teeny tiny because other things can get really close to it.
Right.
So if another water molecule comes by, it might be like, hey, look, I've got a couple of electrons that I could give to you, hydrogen.
Oh.
Yeah?
Okay. Yeah.
Yeah. Yeah. Right now? Oh no, just 4. Maybe you've done less. Yes, you've done less. Yeah. Like I'm happy for you to go to carnivals and enjoy yourself or whatever. Okay. So what you're gonna do is you're gonna say I'm doing methane. And everything else is going to find separate. NA. Plus. That's my negative. Positive ion, my negative ion. So this one equals positive. This has a negative on charge. And then there's states because we're dissociating dissolved in water. What is it? And then for the next one, because there's a 2 beside that K, you're going to end up with 2 Ks instead of just 1 K. The power. And then find the charge on K. Oh, yes. Yeah. Yeah. Oh, okay, so see, private charge. Oh, you're welcome. Yes. Yes. Oh, yeah. There you go.
Thank you.
You're welcome.
So singles chatted
Zinc is not a transition. Well, it is, but it has a definite charge. It's charged.
so is it like
No. Rank-diffs are just for when you're naming something. When it has more than one positive charge, they actually only has one positive charge. Yeah.
I don't know.
so like what is I don't know the gravity of yeah it was like is it like it's not like one yeah so without kind of warms to react as
No. Don't worry too much about the state of originally. You're all going to be dissolved in water, so what happens?
so
So all the products should be. Good. Oh, NH3. NH3, it does not start with, no, it does not start with NH4. Good. Yeah, so you have to pick which one. Yeah. You have to look at one it is. So acids ionic, it will dissociate, molecular, it will disperse.
So yeah, the only parts have was it is all those is it like
Because when it dissolves in water, by definition, anything that is dissolved in water is. Yeah.
so but I still keeps like it's more just what
No,
that's true.
it'll be a mixture, so instead of the CH3OH, staying beside CH3OH, water will go in between them all.
So like it won't form like
It's not even compound, but it's a mixture. Yeah, so it's like if we had. Okay, here's the water, okay? And we have the CH3 COOH, okay? CH3COOH, whatever it is. Those would be together when they dissolve in the water. They separate from each other, but they don't reform. The water gets moving. So when they're in liquid, they're together.
Yeah.
And they pierce their separate. Make sense?
Yeah.
Cool. Happy. Acids or liquids. Yeah. Bases are, yeah, bases are ionic compounds also, so it's not. Yeah.
You can take this.
Yes.
But this take this.
Yeah.
How is it?
Okay. Same thing as all right. All of these black pens are water. Okay. Water. And this is liquid understanding. Okay. So This is the speaker, they're close to each other. When I dissolve it in water, water goes between them. How is it? They're not together anymore. Yeah. If one could show this process. Tyler Witt, if you look at Tyler Witt solutions, we'll show you the difference between molecular solutions and ionic solutions. Yeah, yeah. Folks, if you're having trouble envisioning what's happening with molecular solutions, Tyler DeWitt does a beautiful video on this. I'll find it and I'll post it up on our teams in the general channel. Okay, there's actually a couple of them. One's older, one's newer, but I'll find them for you. That's the one. Ooh, this one's only 4 minutes and 10 seconds. Do you guys want to watch it? Yes? Okay. Do we have time? The bell's not going to ring? No, we got 4 minutes. That's good. Okay, why is it not going? Come on. We got 4 minutes. Come on. Oh my God. Right? Okay, fine. That makes me so unhappy. So I don't know if this is going to come around in time. So I am putting them on Teams. Oh! And by the way, it does not matter if the sugar is solid or if it were a liquid, it works the same way. dissociation. Okay, so you've got your dissociation with the ionic, you've got your dispersion with the covalent. If you want to see what's happening with the water, I've already posted that video, or I will in just a second. Okay, so that would be aqueous solutions dissolving in solvation. It's a little bit longer. It's still not that long, but it goes into more depth, and you can see what's happening with the water as well when things are dissolving, both ionic and covalent. Okay? And I think that's all we got time for today. So homework was 90 to 93 and 42 to 48. Okie dokie, tomorrow will be a review day.
And oh yeah. So if we like put a little electrode and then like heat them up, it's hot. With the wand starts breaking, and so we like two
Possibly, but they'll probably like do something like react, like they'll react with the oxygen in the air.
Oh, actually, then the right.
Right.
So not really like they will put it on the right.
And technically, if you were going to isolate it, you could probably get vaporized, right, to atoms. Like if it's a diamond. Right? In theory, I guess, at some point you could get it to vaporize, but like.
Hard.
Yeah. Yeah, exactly. Okay. See you tomorrow. Huh?
You guys